Walk through the western doors of a Gothic cathedral, before you see the windows, before you notice the columns. Before the vault draws your eye upward, listen. Your first footstep hits the floor, and the floor answers, not with the flat thud of carpet or the hollow tap of wood, but with a sharp, clean report that radiates outward from the point of contact, and returns to you a fraction of a second later, from every hard surface in the building. In that first step, the cathedral has told you what it is, a room built entirely from materials that reflect sound. This is not accidental. It is the foundational acoustic decision of every Gothic cathedral. The floor, typically stone, often marble, occasionally laid in geometric patterns of contrasting stone types, is the largest single horizontal surface in the building, and the one nearest to every sound source. Its absorption coefficient is vanishingly low at the frequencies that matter for the human voice. Sound-striking polished stone rebounds with nearly all its energy intact. A carpeted floor absorbs that energy. A wooden floor transmits some of it downward through vibration. But a stone floor returns it, whole, into the vertical space above, where it begins its journey upward through the column-lined nave, toward the ribbed vault, and back down to chorus again in the long, sustaining, reverberant tail that defines the cathedral's acoustic character. Medieval builders did not have the vocabulary of absorption coefficients or reverberation time, but they knew what a stone floor did to sound, because they heard it every day. The daily office, 5 to 8 hours of sung plain chant, was performed on this floor, in this room. Every decision about the room's surfaces was tested continuously by the most exacting acoustic instrument available, the trained ear of the choir. And the floor was only the beginning. Every surface above it, walls, columns, vault, windows, screens, made its own contribution to the sound. This episode follows that sound upward, surface by surface, through a building where nothing was left to chance. Rise from the floor and look at the walls. In a typical Gothic cathedral, the wall surface is divided into 3 horizontal zones. The arcade at ground level, where massive stone piers carry pointed arches separating the nave from the side aisles. The triforium, a narrow gallery above the arcade, and the clerestory, the uppermost level of windows that admit light from above. Each zone presents a different surface to incoming sound, and each contributes differently to the acoustic result. The stone piers of the arcade are the first vertical surfaces that sound from the floor encounters. These are massive cylindrical or clustered columns of dressed limestone, hard, smooth, and highly reflective. When sound radiating from a singer in the choir reaches these columns, it scatters. The curved surface of a cylindrical pier does not reflect sound in a single predictable direction the way a flat wall would. Instead, it diffuses it, sending reflected energy outward in multiple directions simultaneously. This diffusion is acoustically valuable. It distributes sound energy more evenly throughout the nave, reducing the formation of dead spots and hot spots. The flat wall surfaces between and behind the piers, typically dressed limestone or plastered masonry, behave differently. Flat stone reflects sound in a directional manner. The angle of incidence equals the angle of reflection. These lateral reflections from the side walls arrive at the listener quickly, within the first 50 to 80 milliseconds after the direct sound. Research in architectural acoustics has established that these early lateral reflections create the perception of acoustic envelopment, the sense of being immersed in sound rather than hearing it from a single point. The combination of curved piers that scatter and flat walls that direct produces the characteristic spatial richness of Gothic cathedral acoustics, a sound field that wraps around the listener while simultaneously sustaining itself through multiple reflections from surfaces that absorb almost nothing. Continue upward, past the arcade and the triforium, to the clerestory, the wall of windows. Gothic architecture is defined, more than by any other single feature, by its enormous expanses of glass. The pointed arch and the flying buttress freed the upper walls from structural load-bearing duty, allowing masons to open them into vast window openings filled with stained glass. At Chartres, The clear-story windows rise to nearly 15 meters. At the Sainte-Chapelle in Paris, glass constitutes nearly 3/4 of the wall surface. These windows were designed to admit light, the theological program of the Gothic cathedral as a vessel of divine illumination. But glass is also an acoustic surface, and its behavior is more complex than stone. Stained glass in a Gothic cathedral is thin, typically only a few millimeters thick, and held in place by lead came that divides it into small panels. At high frequencies, this glass behaves much like stone, hard, smooth, and reflective. Treble sounds bounce off it cleanly. But at lower frequencies, the range that carries the fundamental tones of the male singing voice and the bass resonance of organ pipes, something different happens. The glass vibrates. The thin panels flex under the pressure of low-frequency sound waves, and that flexing absorbs energy from the sound field. This means that large Gothic windows function as selective acoustic filters. They preserve high-frequency brightness, the clarity and articulation of consonants in sung text, while absorbing some of the low-frequency energy that, in a building made entirely of stone walls, might accumulate into a muddy, indistinct bass wash. The glass tempers the reverberation. It does not eliminate it. The vast volume of stone surface at the lower levels ensures long reverberation, but it shapes it, biasing the sustained sound toward the mid and upper frequencies where vocal clarity lives. Whether the medieval builders understood this acoustic consequence of their windows is an open question. The windows were designed for light, not for sound, but the acoustic effect is real, measurable, and, once you know to listen for it, audible. Now look straight up. The ribbed vault is the ceiling of a Gothic cathedral, and it is the surface with the most complex acoustic behavior of any element in the building. The evolution from the Romanesque barrel vault to the Gothic pointed ribbed vault was driven by structural necessity. The pointed arch distributes thrust more efficiently, allowing thinner walls and larger windows. But this structural innovation had profound acoustic consequences. A barrel vault is a smooth, continuous curve, and smooth curves focus sound. They concentrate reflected energy along focal lines, creating strong echo effects at some points in the room and dead zones at others. This is the acoustic problem that plague many domed buildings to this day. The ribbed vault solves it. The stone ribs, the structural arches that define the vault's geometry, project below the vault surface. The web panels between the ribs meet at angles. Together they create a ceiling surface that is irregular rather than smooth, scattering incoming sound in many directions, rather than focusing it to a point. The result is diffusion, reflected energy distributed evenly throughout the space below, rather than concentrated in unpredictable hotspots. Research examining acoustic variability across multiple European Gothic churches confirmed that the complexity of vaulting had a measurable effect on sound diffusion. Elaborate multi-ribbed vaults produce notably different acoustic signatures from simpler ceiling geometries. The transition from early to late Gothic vaulting, from simple quadripartite ribs to complex lierne and fan vaults, progressively increased the diffusion of the ceiling surface. For the choir singing below, this mattered enormously. A focusing ceiling produces uneven sound, loud in some seats, inaudible in others. A diffusing ceiling distributes the choir's sound evenly to every position in the nave. The vault did not merely cover the space, it shaped the listening experience for every person beneath it. Move forward through the nave toward the choir. In a medieval cathedral, you would not pass directly from one space to the other. Between them stood a barrier, a choir screen, rood screen, or pulpitum, that divided the building into two acoustically distinct zones. The choir screen was a substantial structure, typically of carved stone or wood, rising several meters high and extending the full width of the nave. Its primary purpose was liturgical, separating the enclosed choir, where the canons or monks performed the daily office, from the public nave. But the acoustic consequence was equally significant. The screen created a room within a room. Behind it, the choir space became a smaller, more intimate acoustic chamber, still reverberant, because the surfaces were still stone, but with a shorter reverberation time due to the reduced volume. The singers heard their own voices more clearly, with faster early reflections from the nearby screen surface, walls, and choir stalls. This produced a tighter, more focused sound environment, ideal for the precise intonation and ensemble coordination that plainchant and polyphony demanded. In the nave, meanwhile, the congregation experienced the choir's sound as filtered through and over the screen. The direct sound was partially blocked. What reached the nave was predominantly the reverberant sound, the sustained, blended wash that had bounced off the choir vault and spilled over the screen's upper edge. This filtering effect softened the sound, removing the hard attack of individual consonants and blending individual voices into a unified texture. The screen thus functioned as an acoustic partition that gave the singers clarity and the listeners beauty. Two different experiences of the same performance, separated by a wall of carved stone. When many of these screens were removed during later centuries, in the name of opening the view from nave to altar, the acoustic character of the cathedral changed with them. The two rooms became one, and the focused intimacy of the choir space was absorbed into the vast reverberant wash of the undivided nave. There is one acoustic feature built into some medieval churches that remains genuinely debated by scholars, and it sits quite literally inside the walls. In approximately 200 churches across Europe, about half of them in France, archaeologists have found ceramic vessels embedded in the masonry. These pots, sometimes called acoustic jars, or by the Greek term Acheia, are built into walls and vaults with their open mouths facing the interior. They range in size and placement, from single rows set at about 3 meters height to clusters arranged in the vaulting above the choir. The idea comes from antiquity. The Roman architect Vitruvius, writing in the 1st century BCE, described bronze vessels placed in theater niches to reinforce the human voice. No ancient examples survive, but his text circulated widely in medieval Europe. The medieval versions differ significantly, ceramic rather than bronze, embedded in walls rather than placed in open niches, but the conceptual lineage is clear. Laboratory measurements of ceramic pots similar to those found in medieval churches have shown that they function as Helmholtz resonators, cavities that resonate at specific frequencies determined by the pot's volume and the dimensions of its opening. Researchers have measured resonant frequencies in the range of approximately 237 to 444 Hz, and found a modest but real effect: slight amplification at the resonant frequency, slight absorption at nearby frequencies, and some degree of sound diffusion. Whether this effect was acoustically significant in a stone church, or whether the jars were placed as a gesture of learned tradition, inspired by readings of Vitruvius, is a question that archaeoacousticians are still working to resolve. Some researchers argue the jars meaningfully tuned the acoustic character of smaller churches. Others note that the effect is too subtle to have mattered in a large reverberant space. A 15th century chronicle from Metz records a prior who ordered pots installed in the choir after seeing them elsewhere, believing they would improve the sound, and another writer who ridiculed him for it. The jars are real. Their effect is measurable. Their builder's intentions remain an open scholarly question. Not every acoustic phenomenon in a historic building was planned. Some of the most striking were discovered by accident and then explained by physics centuries later. The whispering gallery is a phenomenon found in circular or domed spaces, where a whisper produced at one point along a curved wall can be heard clearly at a distant point along the same wall, even though it would be inaudible if spoken across the open center of the room. The most famous example is inside the dome of St. Paul's Cathedral in London, where Sir Christopher Wren's circular gallery at the base of the dome, 30 meters above the crossing, allows a whisper along the wall to carry over 33 meters to the other side. Lord Rayleigh first explained the physics in the 1870s. Sound waves produced close to a concave surface do not spread outward in all directions the way they would in open air. Instead, they cling to the curved wall, reflecting continuously along its surface in a narrow belt. Because the energy stays concentrated near the wall rather than spreading into the volume of the room, the sound decays much more slowly than it would normally, as the inverse of the distance rather than the inverse square. A whisper that would fade to nothing after a few meters in open air can travel the entire circumference of a circular gallery with surprisingly little loss. The key requirements are a smooth, hard, curved surface, stone, marble, tile, or plaster, and a geometry that is circular or nearly so. Rough or porous surfaces scatter and absorb the sound, breaking the chain of reflections. This is why whispering galleries appear almost exclusively in buildings made from the hard, smooth materials that medieval and Renaissance architects favored. Gothic cathedrals do not typically produce this effect in their naves. The straight walls and rectangular plan do not support it. But their domes, apses, and circular chapter houses occasionally do, producing localized acoustic effects that astonished medieval and early modern visitors, long before anyone understood the physics. The whispering gallery is a special case of a broader phenomenon. Curved ceilings interact with sound in ways that flat or ribbed surfaces do not. A dome, whether the full hemisphere of a Byzantine church, the octagonal crossing dome of a Gothic cathedral, or the shallow saucer dome of a Baroque nave ceiling, acts as a concave reflector. Sound waves striking the interior surface of a dome are reflected inward and downward, toward the center of the space below. If the dome is a true hemisphere, this focusing effect is extreme. Sound from a source near the center of the floor is reflected back to virtually the same point, producing a powerful echo. This is why concert halls avoid domed ceilings. The focusing creates hotspots and distortion. In liturgical architecture, however, the effect served a different purpose. A speaker or singer positioned at the center of a domed crossing, the point where nave, transept, and choir intersect, benefited from the dome's focusing. Their voice was reinforced by the reflected energy returning from above, making it louder and more present without any amplification. Gothic cathedrals rarely have true hemispheric domes. More commonly, the crossing is topped by a tower or a lantern with a pointed vault. But the apsidal semicircle at the east end of many cathedrals, the curved wall behind the high altar, does act as a parabolic or semicircular reflector, gathering sound from the altar area and projecting it back toward the nave. This is one reason why the altar position in a medieval cathedral was not arbitrary. It was placed at the acoustic focus of the apse, the point where reflected sound energy from the curved wall behind it was at its maximum. Whether this placement was a conscious acoustic decision or an inherited convention from earlier basilica design is difficult to determine conclusively. But the acoustic effect is real and measurable, and the medieval clergy, who stood at that position daily, would certainly have noticed it. For 8 centuries, everything described in this episode, the reflective floors, the scattering columns, the selective windows, the diffusing vaults, the partitioning screens, the resonating jars, the whispering galleries, the focusing domes, existed as craft knowledge. Builders knew that certain configurations worked. Singers knew which spaces supported their voices, but no one could explain why, in the language of physics. That changed with Wallace Clement Sabine. In 1895, the 27-year-old Harvard physics instructor was asked to investigate why a new lecture hall was acoustically unusable. Working alone between 2 and 6 in the morning, hauling seat cushions in and out of the room to vary the absorption, Sabine derived the first scientific equation in the history of architectural acoustics. T equals 0.61 times F divided by A, where T is the reverberation time, V the room's volume, and A the total absorption. When Sabine's equation was applied retroactively to Gothic cathedrals, it confirmed what the medieval builders had achieved empirically. The proportions they chose, the materials they used, the surfaces they finished, all of it fell within a narrow range of reverberation times optimized for the sustain and blend of the human singing voice. The buildings were tuned, not by theory, but by generations of listening. Modern acoustic researchers have since measured dozens of Gothic churches across Europe, confirming that mid-frequency reverberation times cluster in a predictable range relative to volume, a consistent acoustic signature that holds across different countries, different centuries, and different building stone. The consistency is too tight to be coincidental. It reflects a shared craft tradition, an understanding passed from master to apprentice of what a singing space should sound like. Sabine gave us the equation. The medieval builders had the answer, centuries before the question was asked. If every surface in a Gothic cathedral contributes to its acoustic character, then changing any surface changes the sound. This is exactly what has happened repeatedly over the centuries. Pews were added, rows of wooden seating that absorb low-frequency sound and reduce the reflective area of the stone floor. Carpeting was laid in aisles and chancels. Pipe organs were installed, adding thousands of square feet of wooden and metal surfaces behind the instrument. Choir screens were removed, merging the two acoustic zones the medieval builders had carefully separated. Plaster was applied over raw stone, or removed to expose it. Windows were replaced, some with thicker modern glass that vibrates differently, some with clear glass that changes the light, but also the surface absorption at high frequencies. Each of these modifications shifts the acoustic balance. The effect of any one change may be subtle, but accumulated over centuries, the sum can be substantial. The cathedral a visitor hears today is almost certainly not the cathedral a 13th century monk heard. The geometry is the same. The volume has not changed, but the surfaces, the elements that control how sound interacts with the space, have been modified, often repeatedly, by every generation that has used the building. The restoration of Notre-Dame de Paris after the 2019 fire demonstrated this principle dramatically. The deep cleaning of the stone, removing centuries of candle soot, urban grime, and fire residue, revealed surfaces that were acoustically brighter and more reflective than anything visitors had experienced in living memory. The removal of a 1980s carpet, the replacement of upholstered seating with hardwood, and the restoration of the bare marble floor collectively increased the reverberation. The reopened cathedral was, by some measures, more reverberant than it had been in 50 years, not a return to the pre-fire state, but arguably a return to something closer to the medieval original. Every surface is a decision, and every decision over time is reversible. Stand again at the western entrance. Look the full length of the nave, past the columns and the clear story, past the crossing and the choir to the curved wall of the apse. Every surface between where you stand and that far wall is doing something to the sound in this room. The stone floor is returning energy upward. The cylindrical piers are scattering it laterally. The flat wall surfaces are directing early reflections to wrap around you. The stained glass windows are absorbing low-frequency energy while reflecting treble. The ribbed vault is diffusing reflected sound evenly across the space. The apse is focusing it back toward the nave. And somewhere in the walls of a few hundred churches across Europe, ceramic jars are resonating at specific frequencies, their contribution modest, their purpose still debated. None of these effects was designed using acoustic theory. There was no theory. What there was, instead, was a continuous, iterative process of building, listening, and adjusting. A craft tradition in which the choir was the instrument, the stone was the material, and the builder's ear was the only measurement tool. Over 2 centuries of Gothic construction, this empirical process produced buildings whose acoustic properties are so consistent, so well adapted to the music they were built to support, that modern acousticians studying them can only confirm what the medieval builders already knew. The room worked. Wallace Clement Sabine gave us the mathematics to describe it. Lord Rayleigh gave us the physics to explain the whispering gallery. 21st century researchers have given us digital twins, impulse response measurements, and spectral analysis. But the knowledge came first. The science came after. The builders listened, and the stone remembered. The master masons who set these stones, the glaziers who fitted these windows, the choristers who tested every surface with their voices. Day after day, year after year, they built a room that would carry sound for 800 years. They had no equations, no microphones, no simulation software. They had clay, stone, glass, and an ear trained by a lifetime of listening. That was enough. The buildings they raised are still teaching us how sound works, and they will go on teaching long after we have stopped measuring. There is a subscribe button directly below this video. Pressing it is a small gesture, but it tells us that the real physics and history behind these buildings, the science embedded in the stone, is still something people want to understand. If the acoustic engineering of Gothic cathedrals interest you, subscribe to the channel, and leave us your answers to 2 questions in the comments. Have you ever noticed a space where the acoustics changed the way you heard sound, where the room itself seemed to participate? And which building, which acoustic phenomenon should we examine next?